from where we stopped. So what we will do is like we will continue from where we left off, and essentially, we were looking at equilibrium states, and in yesterday's class, we looked at the concept that if we have a linear system, you and I have, only two choices for equilibrium states. There is, it can be either unique at the origin, or it could be an infinity of equilibrium states or continuum of equilibrium states belonging to the null space of the state matrix. Okay, so that's what we have. But in the case of nonlinear systems, I think what we have is that like we also have a third option, which is the option of multiple isolated equilibrium states. Okay, so that is the essentially the third option as far as nonlinear systems are concerned. So this is the main concept we looked at yesterday. But as we discussed, I essentially talked about nonlinear systems for our information. In this course, we are essentially looking at only the linear systems, right? So we are looking at approximating systems as linear and going ahead with it. But before I forget, before I go into today's content, one important thing. I think Abhinav was talking to me today morning. So when you meet him next Monday, please figure out the date for submitting project number 1. Okay, so I'm requesting Arunachalam to coordinate and decide during the class with Abhinav on Monday evening to fix the final date for project 1 submission. Please do not have it to be too late, okay? Because you also need to have project 2 completed, right? So kindly plan to submit it as soon as possible. Okay, yeah. And Arunachalam, any update on that final exam date?
Sir, today he is going to tell, sir. He is checking with Anand sir, Manivan sir.
Okay.
So today most we will give the date. Based on that, we will fix our date also, sir.
All right. Okay. Fine. So next Tuesday, hopefully, we should be able to. Right.
Sir, okay. One more thing, sir. Coming 25th is our project midday review.
Okay.
So maybe, so it ends. It starts at 2 o'clock and ends most probably nearer to 6 o'clock. So next Tuesday, how we can have the class, sir? That is what.
Next Thursday is the project review, right? Yeah.
No, 2 days, sir. 25 and 27, sir.
So there are 2 batches, sir. So one batch is on 25th and one is on 27th.
Oh, okay. One is on 25th and one is on 27th. Okay, no problem. Then we will have our class on 26th. No issues. Okay, so yeah. Right. I think we will not meet on Tuesday. You can go ahead with your project presentations. We can meet on Wednesday. No problem. Okay. Yeah.
Okay, sir.
I hope that was the query, right, Arunachalam? I hope I answered it, right? Yeah.
Yes, sir.
Okay, fine. But did you have any other proposal in mind?
No, sir. This was the proposal
that
we were also having.
Okay.
Sir, for coming Tuesday, whether you are taking or Abhinav is taking, sir?
No, coming Monday, Abhinav will take. Okay.
Right.
Yeah.
So, okay.
As I told initially, yesterday he was supposed to have taken. So that my meeting got cancelled. So I thought I will anyway meet you. So instead of that, Monday Abhinav will teach. Okay. Yeah. That is 24th of March. So now, as per your input, 25th of March, you are busy with your midterm evaluations, right? Am I correct?
Correct,
right?
Sir, correct.
And so consequently, we will not have our class. So after today's class, we will meet for our theory class next Wednesday at 5 p.m. I hope it's clear, right? So
exactly.
But Monday you need to meet with Abhinav so that you can clarify your doubts on the project. Okay? Yeah.
Sure, sir.
Okay.
Thank you.
All right.
Sir, one thing I want to ask you, typically in the like midterm review of projects, what is the expectation from what I mean to say, sir, from the students in that?
So in fact, what I would broadly suggest is for you to. Did you get any instructions from the mechanical office or the coordinator, for any report submission and?
Yeah, they have asked for some summary of what we have done and what is the progress and all, and some literary references in that way.
Okay. Because
we have to submit one
I
few
came
pages
to
Word document.
I came to know about this presentation only yesterday evening, right? I was told that there is how to say, only yesterday, right? I was told that there's a midterm review. So typically, what happens is that, like, of course, a committee of faculty from the department would be evaluating Roshan, right? And by and large, what they would expect, once again, that's why I asked you the question, did you receive any instructions? So point number one, you should follow the instructions received. If they gave you some indicators on what should be included in the presentation, please do so. Okay. Was that given to you,
Yeah, we've got presentation 15 slides to consolidate, highlighting the progress. And point number 2, max 5 page, we have to write an abstract and then submit, highlighting the literature survey, the works that we have completed, and what we are going to do for the future. So these two indications we have got. What Roshan and we were trying to understand is on two aspects. What will be the expectations from the committee when we are presenting, and
Yeah. So please follow the instructions, and see, by and large, what the committee will try to evaluate. Like, once again, as I told you, this is only an indicative thing to all of you, right? Because please note that every committee is different, right? So, and every presentation is different, right? So even if the same committee, let's say, they evaluate student A, student B, they may ask different questions, right? And come from a different perspective. So kindly be cognizant of that. But then at the broad level, what I can recommend is that, like, a committee would, if I am part of the committee, right? So what I would be looking at is whether the candidate has formulated a problem, right, for their MTech project, and motivated the product, identify the objectives and scope of the work, right, and has a very clear methodology plan, right? And in the methodology, let's say you have certain milestones and like tasks to be done, right? How much have you completed, right? And how much you are yet to complete? You should give a very clear timeline for that, right? So that is what I would expect, right? And if you are able to show some connection to the coursework that you have done, right? So essentially, it's not mandatory, but during the discussion, if you are able to bring out, saying that, look, this concept which I learned in this course helped me to formulate this problem and start solving it, I think that will also be good, because it will show the committee that you have proactively taken the effort to apply what you have learned to a project. Not mandatory, okay, but would certainly help, right? So, okay, all right.
So just an additional question on that. Am I audible?
No, and please, like, I am only sharing all these things only as a well-wisher and a friend. Okay, so please, don't hold me outside and don't hold me to task later. Okay.
We respect the opinion, and that's the reason why we want to ask the question. So just one follow-up on the same thing. How much of depth of technicalities will the panel go into?
See, at the end of the day, Prem, IITM is a technical organization, right?
Yeah,
so we do want to hear specific technical engineering science rather than generic statements being made in the presentation. At least for me, right? Yeah. Okay. Yeah. See, you are getting an MTech from IIT Madras, right? So we are not presenting any other proposal, right? So you are proposing a project which will get us an MTech from IIT Madras, right? So please approach it from that perspective. So kindly, I'm sure your project may have a business use case and so on, but highlight
Yeah, point taken, sir. What just I wanted to see was if we put much of technical content into the presentation and the questions are more into that. So should we go into that direction or not? Is just that.
Yeah. So it is a technical presentation, okay? And you would have been given time limits, so that will also give an indication of how many slides you need to prepare, right? So yeah. So the broad outline of presentation I have already shared, right? So I would always see, once again, I always tell my students, like there's no unique template, okay? So the way we talk, the way we present, the way we write depends on the purpose, okay? One should be able to ready to write a 100-page report, a 1-page note, to give to our boss, right? Like a term sheet, or it should be a 10-page journal paper, right? So we should be ready to write everything in different stages, right? But broadly, what I would recommend is that, like, I always would like to ask these questions, right? What, how, why, how, and when, right? That is, what is the project that I am trying to do, right? Why am I doing it, correct? Then, like, how do I propose to do it? And when do I propose to complete all the milestones? Okay, so when is an additional question for which will propose the timeline, but primarily what, why, how, and when. Okay, so if you are able to answer those questions, right? What is the problem that you are studying? Why are you studying it? Motivated. Then, like, how you propose to study, which will bring the methodology and the steps involved. And then you go and look this one. Okay.
Very clear, sir. Thank you so much.
So thank you so much for giving this perspective, sir. It's amazing. Thank you. Thank you so much.
Yeah. Okay. So I hope I wish the best to all of you, right? And I hope you do well, right?
Thank you, sir.
Thank you so much, sir.
But once again, I'm reiterating, kindly retain the technical flavor. Okay, so what I would say is that, like, like, as an academic institution, Lato, and engineering institution, I would say typically we faculty will focus on the engineering science. Okay, so what do I mean by engineering science? See, since I know only this subject, I am talking about that from the perspective. Let's say you use your project is associated with vehicle dynamics, right? So you want to demonstrate how concepts from dynamics, right, were utilized, right? And talk about vehicle response, like how something was not known a priori, now we have to, right? So that's absolutely fine. All right.
Sir, I agree to all the statement that you have made, but only differ at one statement that you have made is, I know only this subject because I have seen your NPTEL video of IC engines, brakes, everything, and probably you are the man who knows almost everything about automobile.
I think thanks for the comment, Roshan. But then, like, I think it was all like depends on the level of depth that we know. Like, so I learned some things to teach, but question is where can we provide some insights and intuition, right? That's important, right? So I think, but thanks for that feedback. But but I hope all of you got the broad perspective, right? How need to approach it. So keep it technical. That will be my suggestion, right? And and see, if suppose, let's say, see, for example, I will give you an example if it helps, right? Of course, I don't want to take the name of the company, but one of the earliest students, right, the first batch, right? One project was that, like, like in their company, they were having a vehicle where, some instability was happening at some deceleration. Microphone. Yeah. Okay. So, what to say? Some instability was happening at some deceleration, and the model and practice had a nearly 25% deviation. That is, if the theory predicted 0.9 G, right, instability happened at 0.7 G, right, for example, right? So then we used the concepts from vehicle dynamics and showed developed a model which predicted instability to happen around 0.72 G. Okay, so which agreed very well with the reality, right? See, imagine, let's say if I design a vehicle, I tell my customer that, look, instability will not happen until 0.9 G, but in reality, it happened at 0.7 G itself. My customer will be very unhappy, right? So, but by using, the theory that we learned, right? So we were able to reduce the error, right? So the committee was very appreciative of it. Okay, so I'm just giving an example, right? So where you have taken a problem from your day-to-day work, applied the concepts, and then they come up with solutions, right? Yeah. Okay. All right. Okay. So any other questions on the project and evaluation and so on?
Sir, good evening, sir. Myself, Jagan here.
Yes. Yes.
Sir, actually, I'm from marine engineering background. So, so it's mostly on the IC engines that we have for ships, for propulsion and for electrical generation. And so I'm doing with Professor Mallikarjuna sir. So actually, we do not have any R&D facilities in our company. So my the team which I'm working in now is doing the vessel performance analysis. So basically, we will check the operational parameters of engines, and then we will try to optimize as best as possible in order to reduce the fuel consumption. So because our consumptions are massive, so even a small factor of reduction is going to have a greater savings. So ideally, I'm taking the parameters from the ship, the real-time data, and comparing with the test bench data, which I have for that is being done by the maker. So the mini project, basically, I'm doing the ISO corrections for both the test reference as well as the monthly, that is the actual data, and I'm making an interpolation to see what are all the deltas or basically the differences. So I'm referring to certain papers which deals with how the performance optimization can be done and analysis, etc. Sir. So just wanted to ask what kind of defense I need to prepare, sir. I mean, just based on your experience, sir, for such kind of projects, sir.
Yes, Jagan. I understood the broad. So what I can give as a broad input without looking at the details, right? Is that
yes, sir.
So what you can certainly do, like see, engines research is highly empirical. Point number one, right? Because one
yes, sir.
typically uses data and do it. So
Yes, sir.
see, yeah, what I can think of is that like you can maybe first motivate requirement for this, because see, once again we come back to an analogy, right? That is,
Yes, sir.
have a marine engine on board a ship, right, in real conditions.
Yes, sir.
You collect some data and do some evaluation. The
Yes, sir.
parameters that you may get may be different from what you may do on a test bench in a controlled environment, right?
Yes, sir. Correct, sir. Correct, sir.
So what you can do is that, like, by comparing and contrasting the data that you get from both the sources,
Yes, sir.
you perhaps provide insight on why that happens, right? And
Okay,
also,
sir.
you can basically bring in some science into that, right? So you
Okay, sir.
can approach it from that perspective, if that would help.
Yes,
And
sir.
you can propose is that, like, okay, given these discrepancies,
Yes.
how can I maybe propose a method to correct the test bench results for future use? That is,
Okay, sir.
that is also some what to say, perhaps a method that you can propose, right? Out
Okay,
of
sir.
this, right? So yeah, okay, yeah,
Okay, sir. Okay, sir. Sure, sir. Thank you, sir. Thanks for this, sir.
all right, okay, all the best.
Thank you, sir.
Okay, so I think we will get started with our content for today. So essentially, as we are discussing, we are looking at equilibrium states. The question is, what is stability of an equilibrium state, right? So once again, before getting into the math, let's essentially learn from the physics, right? So let's say we have the simple pendulum. Let's say I tap the simple pendulum. What's going to happen? The vertically downward state is the equilibrium state. But if I tap the simple pendulum, it is going to keep on oscillating, right, about that vertical equilibrium state. And in real life, we are also going to have air resistance, right? So if you tap this pendulum, what do you think will happen if I wait long enough?
It will come to a standstill.
So it will come back to the same, vertically downward equilibrium state, right? Is it not, right? So that's what will happen in the long run, okay? So given this, we can immediately observe that, this, you and I can say, hey, look, it is stable, right? In a certain sense, right? Is it not? Okay, this equilibrium state. Okay, and if I perturb it, I am able to come back to the final, equilibrium state as, finally I'm able to come back to the equilibrium state as time keeps on increasing. Okay, so on the other hand, if we consider the inverted pendulum, the equilibrium state is the vertically upward equilibrium state, right? Pi and 0. So now, let's say I tap it. What will happen? It will fall down, right? So imagine the pendulum standing upright. I just tap it, right? Is it going to come back to the vertically upward equilibrium state?
No, sir.
No, right? So it will just fall down due to gravity, right? So in a certain sense, we can immediately observe that it's not going to come back to its original equilibrium state, right? So that is an unstable equilibrium state, right? So I hope this has provided us an intuitive understanding of stability of an equilibrium state. So now we go to the formal definition. Okay, so let's not worry about this epsilon and delta and so on. I'm just giving you the mathematical, formulation just for our information. So what it means is that, like, you take any equilibrium state x star, right? It is stable in the sense of Lyapunov. Okay, so that's a standard term which is used in control systems after the Russian mathematician Alexander Lyapunov, right? Who formulated it. And that's the beauty of mathematics, right? Alexander Lyapunov, formulated it for in a generic sense, but it's also used for automotive applications. Okay, so I think that is the beauty of this theory, right? So what he said was that, like, you have an equilibrium state, x star, it is stable in the sense of Lyapunov if the perturb, okay, so the initial state of the system, right, like tapping the pendulum, right, around the equilibrium state, then the equilibrium state should, or the actual state of the system should remain around the equilibrium state. Okay, that's how I will interpret this mathematical equations involving epsilon and delta. And that happens with, what to say, simple pendulum, right? So the simple pendulum, you and I can see that, when I tap it, I displace the initial state, and then essentially it is going to be around the equilibrium state itself, right? So that's what you and I can immediately observe. Okay, so so essentially, in addition, if the equilibrium state tends, or the state tends to equilibrium state as t tends to infinity, the equilibrium state is said to be asymptotically stable, right? That's what happens with the simple pendulum with air resistance, right? So ultimately, it's what is called asymptotic stability. Okay, so I hope what is called stability and asymptotic stability in this sense is clear. Now we write down the criteria for LTA systems, right? So we consider x dot equals AX. Okay, it is only based on perturbation. Okay, or giving a non-zero initial condition. Okay, so now the point is, if we, the definition of system, the equilibrium state x star is going to be stable in the sense of Lyapunov, if and only if all the eigenvalues of the state matrix have non-positive real parts. That is, the eigenvalues must either have zero real part or negative real part. Okay. So if we consider the complex plane, see, eigenvalues also can be complex, okay, for the state matrix. Sorry, this is the RHP, and this is or the LHP, okay. Then the system is stable, okay. So that is the first result. And if we have any eigenvalues on the imaginary axis, they should be simple. That is, they should not be repeating. Okay, the system has all in the left of complex plane, right? Then the equilibrium state is asymptotically stable. Okay, so real part, the equilibrium state is unstable. Okay, so these are the three results. Okay, and the matrix A is said to be Hurwitz if all its eigenvalues have negative real parts. So if the state matrix, what to say, is Hurwitz, then you and I will know that the equilibrium state is as a consequence. Okay. Now, if we on poles, right? What was the criteria on poles for stability, Bibo stability?
It should remain a LHP, sir.
All poles must lie in the left of complex plane. Okay,
Right, sir.
so that is for this one. So you can see that there is some analogy between that and asymptotic stability of an equilibrium state, because all eigenvalues must lie in the what to say, any poles in the right of complex plane. Then when we have what happens, we have critical stability, right? We have what is called marginal stability or critical stability, right? But in this notion of stability of an imaginary axis, the system is still stable. Okay, so in the sense of Leonardo. Okay, so that is what is an important difference, okay, between that result and what we have learned today. I hope it's clear, right? So once again, let me repeat. If you consider the state space representation and look at stability of an equilibrium state, if we have all eigenvalues of the state matrix to be in the left of complex, we have like all eigenvalues to have non-positive real parts. That is, we should have either a negative real part or a zero real part. Then what happens is with no eigenvalues in the right of plane, it is only stable in the sense of real part. Okay, and if any eigenvalue is in the right of complex plane, it's unstable. Okay, so that is. So now let's apply it to a couple of example problems. Okay, so and then we will see how it how we can interpret it, right? So for the first problem, let's say you and I look at this particular matrix, right? -2, 1, 0, -3. Always we should first calculate the equilibrium state. Okay, so as we already know, you and I calculate the equilibrium state as AX star equals 0. Okay, so when we do that, of course, it's always better to do this calculation, but immediately you and I can see that the equilibrium state is origin. Why? Because the matrix A is invertible. So consequently, the equilibrium state is 0 and 0. It's a unique equilibrium state. If we figure out the eigenvalues of the state matrix, how do we figure out the eigenvalues of a state matrix? We go and solve determinant of A minus lambda I equals 0. If we go and solve that, we get the eigenvalues of this matrix to be -2 and -3. Okay, so that's what we have. Now, the set of eigenvalues of any matrix is what is called as a spectrum of matrix. Okay, state matrix A. So A is the state matrix, and sigma A is the spectrum of the state matrix. So what do we mean by spectrum of the state matrix? It is the set of eigenvalues. Okay, so here the eigenvalues are at -2 and -3. So the spectrum is -2 and -3. Okay, and what can we say? Both eigenvalues on the left of complex plane. So it is what is called asymptotically stable. Okay, so you and I can calculate the eigenvectors also, right? So what are eigenvalues and eigenvectors? This is the definition of eigenvalue and eigenvectors, right? So V is a non-zero vector called as an eigenvector. We have AV to be equal to lambda V. So consequently, we can have A minus lambda I times V to be 0. Then let's say we want to calculate the first eigenvector corresponding to the eigenvalue of -2. We can do this, right? We write A minus lambda 1 I V1 to be equal to 0, right? So if we do the algebra, okay, we will get a V1. Of course, we don't get what to say unique values. Typically, eigenvectors come as span of a vector. That is a multiple, a scalar multiple of a direction, right? Of a vector, right? So we will get V1 to be 0, and V1 can be any scalar C, and that's how we get the first eigenvector. Then similarly, if you and I want to calculate the second eigenvector corresponding to the second eigenvalue of -3, once again we use the same formula, A minus lambda 2 I V2 to be equal to 0, and then we can calculate this as the second eigenvector. Okay, it's some multiple C. SC is a real number multiplying the vector 1 and -1. Okay, so if we want to graphically draw this, okay, let me show you how I constructed this diagram. So let's say in this particular case is a second order system, right? So we have x1 and x2, okay, and this is the origin. So the first eigenvector is along 1 and 0, right? So which is this direction, okay? So 1 and 0 is going to be the real axis, sorry, not the real axis, the horizontal axis, okay? And the direction 1 minus 1 is going to be this line, okay? So, oh, sorry, what is this? 1 minute, sorry about that. Okay, so the direction 1, it's not going away, yeah, 1 minus 1 is going to be this vertical line, okay? So why did we draw the arrows like this? Because in both the cases, these two eigenvectors correspond to eigenvalues which are in the left of complex plane. So the origin is the equilibrium state. So doesn't matter where I start. Okay, I am going to come to the equilibrium state. Okay, so that is why it's called asymptotically stable. Okay, so I will come always to the equilibrium state as t tends to infinity. Okay, so that's what will happen. All right. So that's how you and I can interpret asymptotic stability and also in relation to eigenvectors. Now we will do one more example, okay, where we will see why these eigenvectors also are useful in some cases, right? Now let us say we consider another matrix -2, 1, 0, 1. Let's say we follow the same process, okay? We essentially calculate determinant of A minus lambda I to be 0. You and I will get the eigenvalues to be -2 and 1. Now, what can we observe? -2 is in the left of complex plane, but 1 is in the right of complex plane, right? So consequently, the equilibrium state is unstable as per the criteria that you and I learned. Okay. So, so the bottom line is that, like in this problem, the equilibrium state is unstable. Okay. So then what do we do? So let's calculate the eigenvectors. Let's first calculate the eigenvector V1 corresponding to lambda 1 equals -2. You and I can solve A minus lambda 1 I V1 to be 0. And then we get V1 to be some scalar times the vector 1, 0. Okay, so this algebra, I'm sure it's straightforward, right? So then what we can do is that like we go and calculate V2, which corresponds to lambda 2, okay, which is the next eigenvalue 1. And please note, this is the unstable eigenvalue, right? So this is the eigenvalue for which which is lying in the right of complex plane, and that's right. That's why this equilibrium state was unstable. Okay. So now, if you and I go and calculate for V2, it comes out to be the span of 1 and 3. So, a span of 1 and 3 means it's a scalar multiplying the vector 1 and 3. Okay. So now, once again, if we draw what is called as a phase portrait. Okay. So 1, 0, the vector, it is this horizontal line. Okay. So consequently, since that corresponds to a stable eigenvalue, we put the direction coming towards the origin. The vector 1, 3 is a direction something like this. Okay. Oops, sorry, what happened? Okay, let me redraw that. So the vector 1, 3 is something like this. Okay. So here we put the direction away from the origin. Why? Because this corresponds to an unstable eigenvalue, right? Of 2. That means, like we are going to go away from the origin, right? Due to stability issues, right? Now, how do you and I interpret this, right? So let us say I start from some initial state. Okay, this is my perturbation. Okay, so let us say I have I have the case of, let's say, automated steering, right? So I want to go on a path. I have a deviation from that path, right? So then the question becomes, like, can I come back to the path? So one can motivate application to automotive examples in that manner, right? So let us say, like I'm driving an autonomous car along a certain path, right? But my car currently is somewhere here, right? So there is a deviation from the path, right? So that can be looked at as a perturbation. Then the question is, like whether we come back to the path, right? So in this particular case, since the equilibrium state is unstable, what will happen is that this will go to infinity. This will blow off to infinity along the direction of the eigenvector corresponding to the unstable eigenvalue. Okay, so that is the interpretation. So similarly, let's say we have another initial state which starts here. It will just blow off to infinity along this direction. Okay, so that way this eigenvector analysis will help us, like figure out when an equilibrium state is stable, when it is not stable, and also by figuring out the eigenvectors, you and I will be able to comment on along what direction will the state vector, okay, go to infinity, okay, when we have an unstable equilibrium state. Okay, so those are all some interpretations or inferences that you and I can draw. Okay. Okay, so that's what we would have learned in today's class. So in today's class, basic concept is to look at stability of an equilibrium state. So as far as stability of an equilibrium state is concerned, we have, essentially, if we have a perturbation, then what it means is that, the question is, can the system come back to the equilibrium state, or can it remain bounded around the equilibrium state, right? Then that equilibrium state is stable. Okay. If on the other hand, if the system state comes back asymptotically to the equilibrium state, if we give it enough time, then that's asymptotically stable. Okay. Instability means it won't either remain around the equilibrium state, it will move away from the equilibrium state, right, when perturbed. So we connected them to conditions on the eigenvalues of the state matrix A. For stability, we needed all eigenvalues of matrix A to be non-positive, to have non-positive real parts, and those on the imaginary axis to be simple. For asymptotic stability, we require all eigenvalues of the state matrix to be strictly in the left of complex plane. Okay, and even if one eigenvalue of A is in the right of complex plane, the equilibrium state is unstable. Okay, so these are the three conditions. All right. Okay. So this is what we would have learned in today's class. Any questions on this content, please?
So one question I have. Sir, regarding this phase portrait that you have drawn, sir. So suppose 0, 1 is the case, like where the, like in this slide only, V1 is basically C times the matrix of 1 and 0, right, sir?
Okay.
So 1 and 0, how you are located on the axis, sir? I'm sorry, I could not get
So
that,
1 and 0 means x1 is 1, right? x2 is 0.
Okay.
So where will it come? It will come some,
It will
right?
axis only.
So, but
Okay.
that's any scalar multiple of 1 and 0, Roshan. It could be 10,000, 0 or minus 1 million, 0. That's why I've written the the horizontal axis, right? Okay, I hope that's clear. Right?
And similarly for 1, 3 is basically
okay. So let's say when x1 is 1, x2 will be 3. So you will have the corresponding slope, right? Yeah, that's it.
okay. So
Okay, that's how
tan
you.
inverse something like that, right, sir?
Yeah, yeah. You mark like what we do for straight lines, right? So that's
Okay.
exactly the process. Okay.
Fine, sir. Got it.
Yeah.
Sir, am I audible?
Yes, please.
Just want to understand. So far when we talked about stability, 4 different methods is Bode plots, root locus, Routh criterion, and the Nyquist criterion. But they were all for linear systems, if I'm not majorly linear, or it can be for linear as well as non-linear.
No, let me go. Let's go slowly here, right? What do you mean by 4 criteria for stability? I didn't understand.
Not criteria, the methods in which we analyze stability. My understanding is we used Bode plots. One was root locus, one was Routh's criterion, one was Nyquist criterion. These 4 things we are aware of.
So for stability, we use the Routh's criteria, right? So root locus, yes, yeah, you can interpret when for what values of parameters you will use stability or you recover stability, right? A Bode plot, see, please note, Bode plot and Nyquist plot, it deals with frequency response, where you are starting with the presumption that the system is stable. So I just wanted to clarify that. So
okay.
Clarify your statement. The Routh's criteria is the criteria that you use to check for stability. Okay, when you deal with transfer function representation. Okay, then yeah, root locus, you and I can figure out for what values of certain parameters you will have stability. Okay, so that is what root locus is, right? So then like as far as what to say, transfer function based analysis is concerned, for linear systems you use that. Okay, but please note here also we are dealing with linear systems. Okay, but then we are using the state space representation. I hope that is the difference that I want to convey. Okay?
So one thing is that Lyapunov stability criterion could be applicable for both non-linear as well as linear.
Yeah. So Lyapunov, the definition of stability in the sense of Lyapunov is a generic sense, right? So similarly, even bounded input, bounded output stability frame, the definition is very clear, right? You give any bounded input, the output should be bounded. Okay, that can be applicable even for a non-linear system, right? You and I derive the corresponding criteria for linear systems. That's it.
Also,
So let me summarize. There is a definition of the notion of stability. Then comes the criteria for stability. Definition of stability is what it is, right? That's it. Okay. So, but the criteria for stability, you and I have derived for linear systems. Okay. Let it be Bibo stability or let it be stability in the of an equilibrium state. Okay.
so there was another statement that was made that the system may or may not come to the same point. I don't remember exactly when that was there.
Or what?
There is an optional case of the system returning to the same point.
No, see, okay. So, see, the way stability in the sense of Lyapunov is set up, frame is that you can see, let's say you consider the case of a simple pendulum without friction. Let's say we live in a world where there is no friction, right? Yeah. Okay. So then what do you think will happen?
Infinitely, I can keep oscillating.
Oscillating. So in a certain sense, you will never like come back to the what to say equilibrium state, right? So correct.
Yeah.
Am I correct? You know, like so. Yeah. So, but then the point is, you know, like you have friction, right? You are going to come to you know, like the equilibrium state as t tends to infinity. Okay, so maybe I would have made that statement in that context frame. That is, a system may be stable in the sense of Liouville if it remains around the equilibrium state. It need not be coming back to the equilibrium state, right? But then it can be around the equilibrium state. Okay.
Okay, sir. Okay. Got it. Yeah. Clear. Thank you.
Yeah. Yeah. Any other questions?
Sir, one more thing I want to ask you, like in the traditional way of control system design, when we try to find out the step response of first order system or maybe like second order system in that way, using the transfer function like approach. So do we follow? Do we have any approach for finding the how the system will behave with the step response or maybe ramp response in that sense, input with this type of like method, like a state space method in that sense?
So once again, Roshan, you know, like these are two different streams of analysis, right? Even in the state space representation, you and I can give step inputs, ramp inputs, and step, okay. So essentially, you know, the metrics that come about, you know, like are defined based on figuring out the step response using the transfer function approach, right? But that doesn't prevent us from trying out the step response using the state space representation. Ultimately, please note, the step response is what it is. Okay, so it is the response of a system. Okay, it does not depend on the representation that we use for the system. Okay, so I hope I made it clear, right?
So it
So
is theoretically, sorry.
let us say we have you know, like a mass spring damper system, right? So let us say we use the transfer function representation, right, to essentially get the step response. You and I can also use the state space representation to get the step response. Okay, so you will still have the same response. Okay, irrespective of the representation that you use. Okay, it's only two different pathways to go to the answer.
That is very clear, sir. So just wanted to like ask is like suppose for second order system, the transfer function is omega n square divided by s square plus 2 j omega n plus omega n square. And when we try to figure out what is the response of a space system, then we give ut is equal to, we multiply by 1 by s in that sense, unit response, unit input. And then we get the equation and we try to solve it by fraction, partial fraction approach, and then we get the response of yt is equal to the function of t and all those things. Now, similar way, when we try to write the equation in the state space form, how it would look like, sir? If you can just elaborate with some example.
So if you recall, we wrote down the solutions, right? See, once again, Roshan, that's a good point. The point is, if you recall the state equation, and we wrote down the solution, right? We had e power at x0, then plus 0 to t e power a t minus tau b u tau d tau. You know, like that was the solution to the state equation, right? So now the point is, Roshan, in transfer function, you and I could use pen and paper, right, to do the analysis. If you recall, when in the very first class, you know, how did I motivate classical control and modern control?
Okay.
So I told you that, you know, around 1950s when digital
computer came and then it evolved. Okay.
So solution to ODEs have been there for centuries. Okay, it's nothing new. It is just that the state space representation applied to control systems, right? It is tuned towards, you know, like, you know, like essentially, you know, like the what I will say, the analysis done computationally, okay, rather than by pen and paper. Okay, let me put it that way. Okay, so let me repeat. What I can intuitively tell you is that the analysis for the using the state space representation, the way things are set up, it is more, I will say, convenient to do it using computational methods, right, rather than pen and paper. Okay, so that's how it's set up. Okay, yeah. So of course one can still do it by pen and paper, okay, but then like we need to know a lot of matrix algebra, vector algebra, and calculus to do that, right? So
Sir, the things are very clear now. What you have told, sir. Like, just wanted to just curious about, like, how the equation will look like. Suppose.
No, ultimately, as Roshan, I'm sorry to interject, right? Ultimately, you will get the same solution. Trust me, right?
Yeah, of course, sir.
So,
How it can be different? Yeah.
What happened? Like something went wrong. Okay. Yeah. Ultimately, let's say we have a mass spring damper system, right? I'm just taking a mass spring damper system. Let's say we give a step input, right? You give a unit step input, and we calculate the output, right? Y of t. So let us say you calculate using the transfer function, you get a closed form solution to y of t. You say y of t equals some constant plus something times exponential some p1t plus exponential p. You will get even if you use the state space representative. But then that's where it goes back to our human intangibles, right? So I'm slightly going on a philosophical route here, Roshan, right? So from school, what is the first thing that we learned in mathematics that we are comfortable with, in primary school and all? What would we have learned? We would have learned something of
Addition,
mainly,
subtraction.
yeah, mainly algebra, right? Addition, subtraction. And then like when we come to middle school, we will learn something about geometry, right? And then when do we learn calculus?
In 10th, 11th, 11th, 12th.
11th and 12th, plus 1, plus 2.
11th and 12th, let's say most boards, right? So, and I'm sure all of us are now also exposed to young children, right, in our families, right? So as we age, right? Roshan, I think you can learn mathematics faster than me today, right? Because you are younger, right? Because as we age, right, the capacity to absorb new things also will decay with at different rates for different people. I'm not saying it will decay at the same rate, right? But then what I'm trying to convey is that the algebra that you and I learn at our young age seems easier, right? Is it not? If you recall, even in vehicle dynamics, I made that statement. Why are we converting ODE to algebraic equation using Laplace transform? Because from primary school, you and I are used to algebra. Okay, correct? Point number one. Now, calculus, you and I got used to it only in 11th and 12th. At that time, you and I would have studied for gaining marks, and that's it, right? Depends on how it is taught to us, right? And so it's a matter of what is we are comfortable with also at a very intuitive level, right? So I hope I have given a very circuitous answer to your question because there's no direct answer. The point I am trying to make is that, like, okay, you have a particular system, you want to calculate, let's say, step response, ramp response, impulse response, whatever input you give. You can approach using transfer function. By transfer function, you and I wrote on a sheet of paper, took partial fraction expansion and took inverse Laplace transform and got the solution. Even in state space representation, you can use this equation. What do you need to do? You need to calculate exponentials of a matrix and integral of a matrix, right? One can do that. You will get the same answer. Trust me. Okay. But did we find it easy to calculate an exponential of a matrix?
Of course not, sir.
Why not? Let me ask that question.
Because it was having some component of advanced mathematics, I would say.
What is advanced?
which
It's
involves
only
non-algebraic expressions in that
Ah,
sense.
exactly. Why are we calling it advanced? Because the first thing that we learned was algebra, right? Imagine we live in a world where primary school children are taught, let's say, matrix and calculus, right? And algebra is taught to them, in 11th and 12th. Let's say, I don't know whether it's possible, but philosophically, right? Let's say we construct a philosophical experiment where the sequence in which mathematics is taught is reversed, right? Then would we prefer the state space representation? Most likely, yes. Right? Yeah. Correct? Yeah.
Go ahead, sir.
Okay. So it's just that, the familiarity with which by the way, that reminds me, not related to the scores, but related to this question. If you get a chance, look at the maths textbooks of Eastern European schools. Okay. You'll be amazed at the level of advancement. No wonder Eastern Europeans are good at mathematics, right? So even in primary and late primary, middle schools and all, they learn very advanced mathematics. So I'm once again using the same term, Roshan, advanced mathematics, right? So they learn it in a very formative years itself, right? So they become very good at it, right? Yeah. Fine.
So thank you so much. Thank you so much, sir.
All right. Okay, Roshan. I hope I have broadly answered your query.
Yeah, it's perfectly fine, sir.
All right. Okay.
Thank you. I got the perspective actually.
Oh, it's already close to 6. I don't want to hold you for the next class.
Sir, all are present, sir, not.
Arunachal, all are present? Okay. So,
Yes, sir.
so I'm not even debating what our leader says. If he says all present,
Sir, we never miss your class, sir. That is what.
So,
it is not. Daily we are learning something new, sir.
Okay, yeah. So, I think I'm also having a lot of fun interacting with your batch. So we will meet next Wednesday, okay, as we agree. Okay, so
Thank
all
you.
right. Monday, you please coordinate with Abhinav to have that session. Okay, yeah.
Sure, sir. Sure, sir.
And best wishes to all of
Thank
Thank
you,
you so much, sir. Thank you so much, sir.
Thank you, sir.
Bye, sir.
Thank you, sir.